NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematics video where we'll solve a challenging problem involving polynomials and substitution. Let's look at our example. If x squared plus x plus 1 equals 0, then we need to find the value of 5x to the power 234 minus x to the power 99. Let's start by manipulating our given equation x squared plus x plus 1 equals 0. First, we can rearrange to get negative x squared minus x equals 1. From our rearranged equation, we can also say that x squared equals negative x minus 1. This gives us a way to express x squared in terms of x, which will be useful later for simplifying higher powers. Now, let's find x cubed. We can multiply both sides of x squared equals negative x minus 1 by x. This gives us x cubed equals negative x squared minus x. Then we can substitute x squared equals negative x minus 1 into this equation. This gives us x cubed equals negative times negative x minus 1 minus x, which simplifies to x cubed equals x plus 1 minus x, which equals 1. The result, x cubed equals 1, is very powerful. This means that any power of x that is a multiple of 3 will equal 1. For example, x to the power 3 equals 1. X to the power 6 equals 1, and so on, because x to the power 3k equals 1 to the power k, which equals 1. Now, let's start simplifying our target expression, 5x to the power 234 minus x to the power 99. We need to rewrite these powers in terms of x cubed. Let's start with 5x to the power 234. We can write 234 as 3 times 78. So x to the power 234 equals x to the power 3 times 78, which equals x cubed to the power 78. Since x cubed equals 1, this becomes 1 to the power 78, which is just 1. So 5x to the power 234 equals 5 times 1, which equals 5. Now, let's simplify x to the power 99. We can write 99 as 3 times 33, so x to the power 99 equals x to the power 3 times 33, which equals x cubed to the power 33. Since x cubed equals 1, this becomes 1 to the power 33, which is just 1. Now we can combine our terms to find the value of our original expression. 5x to the power 234 minus x to the power 99 equals 5 minus 1, which equals 4. Let's summarize what we've learned in this problem. First, we started with the equation x squared plus x plus 1 equals 0. We rearranged this to express x squared in terms of x, getting x squared equals negative x minus 1. Then we found that x cubed equals 1, which is a powerful result because it means any power of x that is a multiple of 3 will equal 1. We used this to simplify 5x to the power 234 to 5 and x to the power 99 to 1. Finally, we calculated 5x to the power 234 minus x to the power 99 to get 5 minus 1, which equals 4. Thank you for watching. Thinking Face, here's a quick challenge for you. Try solving a similar problem. If x squared plus x plus 1 equals 0, find the value of x to the power 100 plus x to the power 101. Pause the video if you want to try this challenge yourself. Welcome to our math lesson. Today, we're going to solve a challenging problem involving algebraic fractions and determine the value of an expression based on a given condition. Let's look at our example. We're given that x divided by quantity x squared plus 1 equals a. Then we need to find the value of x squared divided by x to the fourth plus 1. Let's start by writing down the given equation. We have x divided by x squared plus 1 equals a. Let's rearrange the equation by taking the reciprocal of both sides. This gives us x squared plus 1 over x equals 1 over a. Let's expand the fraction on the left side. We can rewrite x squared plus 1 over x as x squared over x plus 1 over x, which simplifies to x plus 1 over x. Now we have x plus 1 over x equals 1 over a. Let's define the expression we're trying to find. Let a equal x squared divided by x to the fourth plus 1. Let's first find the reciprocal of a. 1 over a equals x to the fourth plus 1 over x squared. Let's expand this fraction. 1 over a equals x to the fourth over x squared plus 1 over x squared. This simplifies to x squared plus 1 over x squared. Thinking face now, let's notice something interesting. We can rewrite x squared plus 1 over x squared as the square of the expression x plus 1 over x minus 2. Sparkles, remember, from our earlier steps, we know that x plus 1 over x equals 1 over a. So, 1 over a equals the square of 1 over a minus 2. Next, we simplify this expression. 1 over a equals 1 over a squared minus 2. This equals 1 minus 2 a squared over a squared. Simplifying further, we get 1 minus 2 a squared over a squared. Party popper, finally, let's find a. Taking the reciprocal of both sides, we get a equals a squared over 1 minus 2 a squared. Therefore, our final answer is x squared over x to the fourth plus 1 equals a squared over 1 minus 2 a squared. Let's summarize what we've learned in this problem. Thank you for watching. This problem demonstrates the power of algebraic manipulation and substitution in solving complex fraction problems. Practice similar problems to strengthen your skills in handling algebraic fractions. Welcome to this math tutorial. Today, we'll solve a problem involving algebraic manipulation of expressions. We're given that x minus 1 over x equals 4, where x is greater than 0. Our task is to find the value of x squared minus 1 over x squared. Let's start by recalling a useful algebraic identity. The square of a difference equals the square of the first term, minus twice the product of the terms, plus the square of the second term. Now, let's apply this by squaring both sides of our equation. On the left side, we get x squared minus 2 times x times 1 over x plus 1 over x squared. The middle term simplifies to just negative 2. On the right side, we get 4 squared, which is 16. Now we can rearrange to isolate x squared plus 1 over x squared, which equals 18. Now, let's observe another useful algebraic identity. The square of a sum equals the square of the first term plus twice the product of the terms, plus the square of the second term. We can use this to find the value of x plus 1 over x. The square of x plus 1 over x equals x squared plus 2 times x times 1 over x plus 1 over x squared. This simplifies to x squared plus 2 plus 1 over x squared. But we already know that x squared plus 1 over x squared equals 18. So the square of x plus 1 over x equals 18 plus 2, which is 20, taking the square root of both sides. And since x is positive, we get x plus 1 over x equals the square root of 20, which simplifies to 2 times the square root of 5. We're now ready to find the answer to our original question. Let's recall the difference of squares formula. A squared minus b squared equals a plus b times a minus b. We want to find x squared minus 1 over x squared. Using the difference of squares formula, this equals x plus 1 over x times x minus 1 over x. But we already know that x plus 1 over x equals 2 times the square root of 5, and x minus 1 over x equals 4. So our answer is 4 times 2 times the square root of 5, which simplifies to 8 times the square root of 5. Let's summarize what we've learned. Welcome to this mathematics video, where we'll work through an interesting algebraic proof. In this problem, we need to prove that if a plus b equals 1, then a squared times a plus 1 plus b squared times b plus 1 equals 2 minus 5 times a times b. Let's start by understanding what we know. We're given that a plus b equals 1. This means that we can express b as 1 minus a, or alternatively, as 1 minus b. Now, let's look at the left side of the equation we want to prove. We start with a squared times a plus 1 plus b squared times b plus 1. For the next step, we'll substitute our expressions for a and b. Since it equals 1 minus b and b equals 1 minus a, we can rewrite our expression as a squared times open bracket 1 minus b plus 1 close bracket plus b squared times open bracket 1 minus a plus 1 close bracket. Simplifying inside the brackets, we get a squared times 2 minus b plus b squared times 2 minus a. Let's continue by expanding this expression. We multiply a squared by 2 minus b, which gives us 2 a squared minus a squared b. Similarly, we multiply b squared by 2 minus a, which gives us 2b squared minus ab squared. Combining these terms, we get 2 a squared minus a squared b plus 2b squared minus ab squared. For the next step, let's try to factor out some common terms. We can rearrange this as 2 times a squared plus b squared minus ab times a plus b. Since we know that a plus b equals 1, we can substitute this into our expression. This gives us 2 times a squared plus b squared minus ab times 1. Let's continue simplifying. This gives us 2 times a squared plus b squared minus ab. Now, we'll use the identity that a squared plus b squared equals open bracket, a plus b close bracket squared minus 2ab. Since a plus b equals 1, we have open bracket, a plus b close bracket squared equals 1 squared, which is 1. So, a squared plus b squared equals 1 minus 2ab. Now, we substitute a squared plus b squared equals 1 minus 2ab back into our main expression. We get 2 times open bracket, 1 minus 2ab close bracket minus ab. Expanding this, we get 2 minus 4ab minus ab. Combining like terms, we get 2 minus 5ab. And there we have it. We've successfully proven that if a plus b equals 1, then a squared times a plus 1 plus b squared times b plus 1 equals 2 minus 5ab. Let's quickly summarize what we did. First, we used the given condition that a plus b equals 1. Then we expressed the left side of our target equation in terms of a and b. We expanded and factored strategically. We used the identity for a squared plus b squared. And finally, we substituted and simplified to get our desired result. This is a powerful technique used to solve equations that might initially look challenging. Let's start with our first example. We need to find the values of x and y that satisfy this equation. Let's analyze this step by step. Our first step is to rearrange the equation by grouping related terms. We'll group the terms with x squared and xy together, and then group the terms with y squared together, and finally group the terms with just x and constants. This gives you s. Now, we need to recognize some perfect square patterns. Let's look at the first group of terms x squared minus 2x, y plus y squared. This is actually the perfect square of x minus y, which equals x minus y squared. Now, let's think about what this means. We have the sum of 2 squared terms equals 0. Since squares are always non-negative, the only way their sum can be 0 is if each term individually equals 0. So we get two equations x minus y equals 0, which means x equals y. Combining these results, we know that x equals 3 and y equals x, so y also equals 3. Now, let's tackle a more challenging example. This time we have an equation in 3 variables x, y, and z. We need to find all 3 values. Let's apply a similar approach. As before, we'll start by grouping related terms. We'll group terms with x, then terms with y, and finally terms with z. Let's rewrite the equation as. Now, we need to complete the square for each variable. For the x terms, we have. Again, we have the sum of squared terms equals 0. Since squares are always non-negative, each term must be 0. So we get 3 equations x minus 2 equals 0, which means x equals 2y plus. Our solution is x equals 2, y equals negative 3, and z equals 4. Let's summarize what we've learned about completing the square to solve equations. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.